building associated to maybe just GLN F. I should say the affine building, not the usual building. And I will start by recalling some facts about valuation rings. And I believe that most of you have seen it. Nevertheless, I'm told that not everyone know this, so I will recall some of the definitions. So, valuation rings. Before I start, I should say that what I'm going to do could be done in greater generality. I would only focus in what needed for this lecture. So the context is this. So definition: F is a field, an additive discrete valuation on F is a map V from F star, namely F without 0 to C. I require it to be onto. It doesn't matter so much, such that 1, V of AB is V of A plus V of B. 2, V of A plus B is greater or equal than the minimum of VA and VB. And third condition, oh, that's it. Yes. And we sometimes we set V of 0 to be infinity. And with every valuation, I should say this is a discrete. I wrote this. I should say that with every evaluation comes a valuation ring. So we define V, this is the valuation ring. To be all those elements of F whose valuation is greater or equal to 0. And perhaps the first claim. Well, O is a ring. And also, the units of O are those elements of F whose valuation is 0, precisely. And so let I F be such that valuation of pi is 1, then the ideals of O are following: just O, pi squared O, etc., and 0. That's it.
O star means the invertible?
This means the units, invertible elements in O. And the proof is actually very easy. Everything follows pretty straightforward. So that O is a ring, we only need to verify that. So 1 is an O since V of 1 is V of 1 times 1, which is V of 1 plus V of 1. And that means that V of 1 is 0. Likewise, minus 1 is in O. And if A and B are in O, then V of AB is V of A plus V of B, which is greater than 0 because each of these is greater than 0. And this means AB is in O. And likewise, A plus B, so A, B in O implies that A plus B is in O. I just use this axiom to show this. This is clear. So this is 1. What about the units of O? So let's start with, so if the valuation of x is 0, then the valuation of x to the minus 1, which is an element of f, but a priori not an element of O, is just the minus of the valuation of x, which is 0. This implies that x to the minus 1 belongs to O, and hence x, well, and hence x is a unit of O. In the other direction, if x is invariable in O, so let y be x to the minus 1, also in O. So this is x to the minus 1 in f. It has to coincide with the inverse in f. Then the valuation of x and the valuation of y is greater or equal to 0, but the valuation of xy, this is the valuation of 1, which is 0. On the other hand, this is the valuation of x plus the valuation of y. And this forces that the valuation of x equals the valuation of y equals 0. So this completes the proof of 2. Any questions about this? We're just recalling this. To those who came now, we recall some definitions and basic results about valuation rings. What about 3? So let I be an ideal of O. Let us suppose that I is not a 0 ideal, otherwise we are done. Take some x in I such that v of x is minimal. V of x takes values in the natural numbers, hence there exists some such x like this. And let n be the valuation of x, then pi to the minus n, the valuation of pi to the minus n x is the valuation of pi times minus n plus the valuation of x, which is just minus n plus n. This is 0. And by 1, this means that pi to the minus n x is a unit in O. This means that x times, well, pi to the minus n x to the minus 1, which is also an element of O. This belongs to I. However, this is just pi to the n. So I to the n O is contained in I. On the other hand, if y is any other element of I, then the valuation of y must be greater or equal to the valuation of x, which is n. This implies that the valuation of pi to the minus n y is, let's see, should say y to the pi to the minus n y. This is n minus value n minus n plus the valuation of y. This is greater or equal than 0, so pi to the n pi to the minus n y belongs to O, and this means y is in pi to the n O. So I just showed the inverse inclusion, so we conclude that I is pi to the n O. This completes the proof. This is all very, I would say, standard. Any questions about this? You don't have to remember all the proofs in detail. It's very easy to recover them. But we will use the three properties that I wrote here, 1, 2, and 3. Okay, so another property of additive valuations is that they induce what is called a norm or a multiplicative valuation on the field. So here's another claim. So fix some epsilon real number between 0 and 1, and let the absolute value of x, an element of f, with respect to v, set it to be epsilon to v of x. And also let the distance of x and y to be the difference, the absolute value of x minus y. Then F becomes a metric space with respect to D. It doesn't matter which epsilon you take. The topologies induced on the field are equivalent. I will not prove this. This is just technical, and it follows from the axioms, which I just erased. So I don't know, I will leave it as an exercise. I will just comment, so remark, this function E of b from f to, in this case, it's going to be r greater or equal 0 satisfies, I should say f star to r greater than 0. It satisfies the following two conditions. So the absolute value of xy is just the absolute value of x times the absolute value of y, and the absolute value of x plus y is less than or equal to the maximum of the absolute value of x and the absolute value of y. And we usually set that the absolute value of 0 is 0 also. So set and this absolute value, any function that satisfies these axioms, is called a multiplicative valuation. So with every discrete valuation is associated a multiplicative valuation. Say this is a non-Archimedean valuation, so this is there is the triangle inequality, so which says that it should be less or equal than from the absolute value of x plus the absolute value of y. This is significantly stronger. Anyway, let us see some examples. So the first example is f would be the rational numbers, and p would be some prime number. And I will define Vp from Q star to Z as follows. So Vp of A over Vp to the m. So here A and B are co-prime to P, and m is an integer. So I could always write a rational number as a pth power and the quotient of two co-prime of two integers which are co-prime to P. This presentation is unique, so I will define this to be n. So for example, I could take, for instance, I equals P satisfies Vp of P equals 1. And what is the valuation ring? OVP or OP. So this is just all the irrational numbers m over n such that n is co-prime to P. So these numbers are precisely those numbers whose valuation is greater or equal to 0. This is easy to see. If you like, you could just write Z 1 over Q. So Q is prime, Q is not P, and also another description. And another example, I want to leave here some blank space. Another example, this time in positive characteristics. So take F to be, let us take some finite field with P elements and adjoin incidental element T. And I will define V from F star to Z by as follows. V of Ft over Gt. So this is the order, this is a rational function, a quotient of two polynomials. This is the order of the zero or pole at t equals 0. And if you want more explicit definition, so write this as Ft, Gt, F tilde t, G tilde t times t to the m. So this would be m, where these are z satisfy F tilde of 0 and G tilde of 0 are non-zero. So I could always extract power of t, and this power would be the valuation. Again, for example, if I take pi equals t, satisfies valuation of t equals 1. If you want example, for example, what would be the valuation of t plus 1? Anyone? Valuation of t plus 1?
0.
0. Because I just have to write it, I mean, I should factor my polynomials and take out the largest power of t that I can. So the valuation of t plus 1 is going to be 0. Also in this example, say p equals 2. So the valuation of 3, for instance, would be 0. I only care about powers of 2. So I don't know, the valuation of 8 is going to be 3 because 8 is 2 to the third. Okay? You see that there is something in common between these two examples. Namely, I focus on some prime element, and I ask what is the multiplicity of that prime factor in my number. This I take to be the valuation, and essentially, I should say that all discrete valuations are of this form in a certain sense. Okay, and so, anyway, what is the valuation ring here? The valuation ring is just the polynomial ring. That's it. Oh, no, I'm sorry. No. Okay. Sorry, the valuation ring is f of t over g of t with ft and gt polynomials such that g of 0 is not 0. This is the valuation ring. So rational functions without a hole in 0, namely. Well, this is obvious from this description. And the ideals of this ring are going to be O, T O, T squared O, T to the third O, etc. by what we have shown. Any questions? Okay. So here's another remark. We can complete F as a topological space with respect to the metric D. The resulting the resulting metric space, which I will denote by FV, is again a field and V extends to FV by the following formula. So every element of FV is a limit of elements of F. These are elements of F. So V of this limit is just going to be, sorry, n tends to infinity. This is just going to be the limit of V of xn. And again, we get a valuation ring, and everything works the same. So here, I told you I want to leave a blank space. So the completion of Q at dp is QP. These are the p-adic numbers. I would give another description shortly, but here, what would be the completion? The completion here. So the completion of FPP at V is what is sometimes known as the field of Lorentz series. What is this? This is the field of all formal power series, AI t to the I, with I ranging from some integer m to infinity. So AI is an element of Fp, and m is some integer. This turns out to be the completion. I see people wince. And do you want to ask anything about this? We won't need completions in this case, but it's always good to know the definitions of the p-adic numbers and get familiar with these kind of rings, power series, to those of you who did not see it before. So you could multiply power series in some fashion. The way to embed FPT inside this ring is just taking the Lorentz series of the polynomial of the rational function around 0. This works. Anyway, if you're not satisfied with the description I gave you of the p-adic numbers, so another descriptions of QP and also ZP, which is the valuation ring of QP. These are called the p-adic integers. So you could think of QP as just formal power series AI to the AM p to the m plus a m plus 1 p to the m plus 1 a m plus 2 p to the m plus 2 and so on forever, where AI lives in 0 to p minus 1, and m is some integer. And ZP is going to be the same, just with m greater or equal to 0. So you could, I would say that another way to think of the p-adic numbers is like numbers, I don't know, like decimal numbers in base p, but instead of allowing infinitely many digits after the point, you allow infinitely many digits before the point. So I don't know, 0, 2, 0, 1, 2, 3, 1, 3, 2, 0, 2, 3. So I don't know, this is like a five-adic number, if you like. Okay, this could be understood as this kind of power series. And if you want -1 in this representation, so I only allow positive numbers. So how do I get negatives? So I do get negatives. -1 is just p minus 1 plus p minus 1 times e plus p minus 1 times p squared, etc. You could check that it works. I mean, if you add 1, so let's say you add 1, which is just 1 plus 0p plus 0p squared, so this cancels out, and you get something here, which cancel out this one, which cancel out this one, etc. So this is indeed -1. I know it's weird, to those who see it for the first time. There is another way to describe ZP. This is the inverse limit. To those of you who know, so this is there is this series of groups. Here you just do mod p squared, and this series lasts forever. So this is the inverse limit of this series. If you don't know what is inverse limit, so forget about it. Okay, this is all I wanted to say about valuation rings. Any questions?
So yeah, the description you have there of the p-adic numbers is sort of similar to what you have on top of the FPT, whatever you call it.
Yes.
So what is the connection between them?
You could do this kind of description for every discrete valuation ring. So oh, I did not, I almost forgot. This is good. I want to erase this. So if we return to the general context, notice that pi o is a maximal ideal of O, right? Because there is no ideal between them. And this implies that O over pi O is a field. Let's call it K. This is a field, and it is called the residue field. And what you do, you take a set of representatives to the residue field, and you take power series, and this roughly gives you O if you start from power series beginning from 0, or F, power series beginning from some negative integer. So you could roughly take power series in K in some sense.
And the difference is characteristic.
Yes, there is a difference of characteristic. I mean, you can't take power series in general, but you could almost take, I mean, you could take representatives to the cosets of pi O in O, and take formal power series in these.
I mean, the main difference between QP and FP.
So the main difference is that these guys, I mean, these powers interact with each other. This is the main difference. And in the case of power series, they do not really interact with each other. So, I mean, here I add 1 and I gain 1 here, for example.
So the multiplication in both is not the same.
No, of course not. So this is like decimal multiplication. Multiplication is very different. Anyway, don't put your mind too much to it. Let us proceed. Okay. So from now on, I'm going to set some general notation. So henceforth, F is a field, V from F star to Z is a discrete valuation. O is the ring of integers, the valuation ring. Recall that these are all the elements of F with Vx greater or equal to 0. Pi is a uniformizer, namely V of pi is 1. And little k is going to be O over pi of O. This is the residual. And what I now want to talk about is lattices. Okay, so definition. Oh, I should also say D is a fixed greater or equal than 2. D is a fixed integer. So definition, a lattice, or I should say an O lattice in F to the D erase this. Is a finitely generated co-module L contained in F to the D such that L contains a basis of F to the D. Or alternatively, F times L, meaning all linear combinations. This gives you all of F to the D. Okay, let me give an example. So example, by the way, do everyone know what is a module? So it's like a vector space, but with rings. Same axioms. Only difference is that you do not get a dimension in general. However, in this case, you do. I mean, in this special case of O. So an example is O to the D. Okay, it is contained in F to the D. That's a lattice. As you see, it is finitely generated over O because this is just the span. If I take the standard basis, OE, this is the standard basis. So it indeed spans this. So this is finitely generated over O. And it contains the basis of F, namely the standard basis. Another example. So let V1 to VD be an F basis of F to the D, then L equals OV1 plus OV2 plus OVD is a basis, is a lattice. Again, finitely generated, contains a basis. this is clear, finitely generated, but everything is a linear combination with coefficients in O of some finitely many vectors, and it contains a basis, obvious, and with this basis. And
Isn't that all these examples?
yeah, so all lattices are of this form. So in fact, I'm not going to prove it. This is an exercise. All lattices are of this form. And we say, so if L is just OV1 plus OVN, OVD, and V1 to VD is a basis of F to the D, I should say an F basis, then we say that V1 to VD is a basis of L. So this is just to make things comfortable. So like vector spaces have bases, so lattices inside finite dimensional vector spaces have bases. And there is a very useful lemma, very well-known lemma that I want to mention. So if L1 is contained in L2 are both lattices in F to D, then there exists a basis V1 to VD of L1, L2, sorry, and integers N1 to ND such that L1 is pi to the N1O, V1, maybe I should change the order. So this is O pi to the N1 V1 plus O pi to the N2 V2 plus etc. plus O pi to the ND VD. So this theorem is true in any unique factorization domain, not unique factorization domain. This is true in every Euclidean domain and also in Dedekind domains. In the case of valuation rings, in the special case of valuation rings, it is very easy to prove it. So let me give the proof.
What we say?
Sorry.
What we say?
So the thing is that I could choose a basis to L2 such that I could choose bases of L2 and L1 such that I get one basis from the other by multiplying by powers of pi. It's comfortable. I mean, this is useful for computations. That's all. I mean, this is a very general principle, so I would sketch the proof. What's the hour? Sketch. So choose basis V1 to VD of L2, U1 to UD of L1, and write the transition matrix. So what is the transition matrix? I just write Qi is sum of alpha ij vj, and I get this matrix. This is the transition matrix, so alpha 1, 1, alpha 1d, alpha dd, alpha d1. And what I actually want to show, so all these are elements. This is a matrix over O, right? It's a matrix over O. So all I want to show is that I could choose this matrix to be diagonal. Okay, now I could, so the thing is, I could apply row and column operations. So if I change the bases here, if I change these two bases, then it's the same like applying row operation and column operations. Is this clear? This is just changing the bases. I don't know, if I replace v1 by v1 plus v2, then I think in this notation, okay, don't catch me by the word, but I think it's going to be a column operation. And if I change this basis, for example, then it's going to be a row operation. And I'm claiming that using elementary row and column operations, I could make this matrix diagonal. So how do I do that? So write all the valuations. So this is the valuation matrix. So I get a lot of integers. I don't know, this is nij. So take the largest, take the smallest valuation. Okay, so I don't know, take nij, this would be the smallest valuation, and put it in the corner, okay? So this is going to be the smallest valuation. Okay, now, since this has the smallest valuation, it divides everyone. So I could use it to kill all these. I'm going to get zeros here and here. I could use it to kill all these, and then I proceed by induction. So this is a sketch of the proof. So I won't give you the details. If you want the details, then you could, I don't know, write it yourself. I don't think I've ever seen it in full detail except in maybe Rainer's book. Anyway, this technique is very general. It works in a much more broader context. For instance, it works if you take z lattices inside R to the n. Same thing works. Any questions about this? Okay. So I think we'll take a 10 minutes break and then proceed.